Hello everyone and welcome to MV Tutors. I'm Solo and I'll be continuing with you guys on electrochemical cells. So last time we had a look at electrolytic cells, and today we'll be having a look at, or focusing rather, on the galvanic or voltaic cell. Okay, so while we're at it, please don't forget to like our videos and also subscribe to our channel. Okay, if you guys want to have a private lesson, please go to our website and make a booking on www.mvtutors.co.za. All right, so yeah, let us see what this has in store for us. And please also don't forget to share these videos, especially with those who will be in matric next year or those who will be upgrading. And yeah, guys, I'm a little bit under the weather, so please don't mind me and my blocked nose today. Okay, so what exactly are galvanic cells or voltaic cells? Well, basically, they are electrochemical cells where the chemical energy is converted to electrical energy. And this kind of chemical reaction, it actually takes place spontaneously. So, what does it mean when we say it takes place spontaneously? Well, it is self-sustaining, okay? Or else we could say it doesn't have to take place with the addition of another energy source. Okay, and an example would typically be your batteries. Okay, so here we have a voltaic cell, okay, or a galvanic cell. I'll probably keep saying this or that, galvanic or voltaic. And I hope you realize that the difference between it and an electrolytic cell is with the electrolytic cell, you only had one beaker, if I could say. Here you have two of them, okay, and we refer to them as half cells. All right, so on one side you have the anode, okay, on the left hand side, and on the right hand side you have the cathode. Guys, they can put it in any way. They can put it the cathode on the left hand side or the anode on the right hand side. It doesn't matter. It's just the way I have drawn it for you guys. It's just the anode is on the left and the cathode is on the right. Okay, so what happens exactly? Remember, with the electrolytic cell, the anode was positively charged, and it was only positively charged because it was connected to the positive terminal of the battery. But here, actually in its natural state, because this happens spontaneously, your anode is negatively charged. So why is the anode negative? Well, it's negative because it is, or rather it has a negative electric potential when you compare it, or as opposed to your electrolyte. Okay, so you have your electrolyte in there. Okay, and we'll just discuss shortly what happens, what kind of electrolyte you should use, and so forth. Well, yeah, so basically it's negatively charged because it has a negative electric potential compared to your solution or your electrolyte. Okay, and another thing is, because of the anode, remember, that is basically where oxidation occurs. I don't know if you remember my little aura there that we discussed with the electrolytic cell. Okay, well, basically at the anode, with the help of the reducing agent, you get oxidation. Okay, so oxidation occurs. And what is oxidation? Oxidation basically is the loss of electrons. So here at the anode, you keep losing electrons, okay? I wanted to use the yellow color, but let's just stick with blue. So your electrons are actually coating your anode, okay? And as they are coating your anode, again, your anode will be it will be negatively charged, okay? So the electrons are leaving, while you have, let me just choose X, while you have the metal, when it undergoes oxidation, it produces cations. Okay, it produces positive ions in the electrolyte. Okay, so that is basically what happens at the anode. It is negatively charged because it has a negative potential with when you compare it with the electrolyte. The electrolyte has a positive, right? It has positive cations. So yeah, the anode has negative. It is negatively charged. Okay, and then as it loses electrons, those electrons that are readily going out and they are coating the anode, they go all the way to the cathode. And the cathode is positively charged. So in here, you also have positive ions, okay? Your anions. And you also have your electrolyte that's there. We're going to talk about the electrolyte shortly. So it is positively charged because you actually have your cations surrounding. Okay, they are surrounding, basically they are coating at the moment your cathode, okay? And so it is positively charged. So it is when the electrons are actually moving all the way to the cathode that those positive ions actually become reduced. Okay, they become reduced to metal. All right, so that's why in essence your anode will start losing mass. Okay, because it is giving away electrons and positive ions are in the electrolyte, so it will lose mass, whereas your cathode will gain mass. Okay, it will gain mass. Why? Because your cations that were surrounding it, hence it's positive, will be reduced as soon as the electrons come in. So yeah, that's basically what happens. So you have your two half cells, your anode, which is negatively charged, your cathode, which is positively charged, and you have a voltmeter that measures the potential difference as this electrical as this chemical process takes place. Okay, so a voltmeter will measure the potential difference, so it will give you the EMF, electromotive force. Okay, and then there's this thing here in the center. Okay, the salt bridge. Okay, so what is the salt bridge? We're also going to get into detail with it. Well, basically, in simple terms, it connects the two half cells and it completes the whole circuit. Remember, electrons are flowing, there's a chemical process, and electricity has to be produced. So there has to be something that's connecting the two half cells, and that is the salt bridge. And inside the salt bridge, you actually have a type of salt, maybe like sodium chloride or potassium chloride, or maybe potassium nitrate. We're going to get into it. And you also have here, I hope you see, you have what we call a cotton plug. Okay, so basically it tries to restrict what is inside the salt bridge, the solution, the aqueous solution, that the salt that you have in the salt bridge. It's sort of like, not that it prevents it from coming out, it will come out eventually, okay, but the rate at which it comes out, so it sort of like blocks it, but it also prevents your cations that are in your anode or your half cells from coming inside the bridge, the salt bridge. Okay, so yes, and like we said, with the anode, my aura there at the anode, with the help of the reducing agent, that's where oxidation occurs. Or if you can't remember that, there's always an ox. At the anode, oxidation occurs. Or on this side, if you remember, what did I have there? Core. Okay, or rock. I had rock. I forgot my own stuff. So you have rock there. Okay, so basically at the cathode, with the assistance of the oxidizing agent, you get reduction. And we spoke about it, that you have your positive cations coating your cathode. With the assistance of electrons coming through, those cations are reduced to metal. Okay, and yeah, am I missing anything? I think that's pretty much what you have here. So also in here you have your electrolyte. Okay, and then so this whole reaction, actually, when it comes to galvanic cells, it is exothermic. If you have electrolytic cells, it is endothermic. So with exothermic reactions, when that's basically where you have your enthalpy being less than 0. Okay, and then here, guys, when you have a reading from your voltmeter, when it comes to voltaic cells, it will always be positive. It must be positive. If you get a negative reading, then something went wrong. Okay, with electrolytic cells, however, it was negative, right? So it was always negative. So please make sure when you do your calculations and you're calculating the E naught cell or E cell, that you always get a value above 0, not below 0. Please, please, please. So yes, I wanted to talk about the electrolyte. So the electrolyte that you would have in both your half cells, one thing you should ensure if you were to choose what kind of electrolyte to have, you must ensure that the electrolyte is soluble. Guys, we do not want to have precipitates forming. And if you forgot, really, just go look at the solubility rules, okay, so that you know which compounds are actually soluble and which are not, and different combinations. So for one, your nitrates, that is NO3 minus, those are always soluble, okay? And most of the sulfates, which is SO42 minus, they are also soluble, most of them. Okay, there are conditions. But the safest one to use as an electrolyte, okay, in both your half cells is the nitrate. You can also use it in your salt bridge, okay? And you don't want to have silver. Maybe you have a silver electrode and it starts forming silver ions in the electrolyte. You don't want to use what is that one that forms a precipitate with silver? But chloride. So you don't want to have an electrolyte where you have chlorine, for example, in it, because chlorine and silver, they actually form a precipitate. So please just make sure you know your solubility rules, so that if they were to ask you what kind of electrolyte should you have in there, you know that you want an electrolyte that is always soluble. And the salt bridge. So what is the function? Like I said, it joins the two half cells, okay? And it completes the circuit, okay? And it also contains an electrolyte with spectator ions. So like I said in here, you could have like potassium chloride, okay, or potassium nitrate. Let's just go with potassium chloride. Okay, potassium has a positive charge, the chloride ion has a negative charge. So let's just say you have your ions in there, okay, and these ions, remember, they can pass through the cotton plug. They can pass through the cotton plug. Also the salt bridge, sometimes it would be somewhat permeable, okay. So basically these electrolytes, they are very weak, okay, because once they get into your half cells, okay, you don't want a scenario where you have your electrolyte and the salt from your salt bridge now competing to be oxidized, okay. You don't want that. So basically they are weak oxidizing agents as well as weak reducing agents, okay. And the reason why you would have a salt bridge is you would want, once this whole chemical process starts to occur, you will have a chemical imbalance. You actually, your voltmeter reading at some point will, give readings that are not there. So what you want the movement of these spectator ions to ensure that there is neutrality in both the half cells. So what do I mean by maintaining neutrality? Okay, this is where the importance of a salt bridge comes in. So basically, at your cathode, no, not your cathode, where you have your anode, the half cell there, remember, your metal here will be oxidized, and as a result, you will have cations forming, okay? So your half cell here will be positively charged, okay? It's not neutral anymore. Before the voltmeter is connected and this whole chemical process is happening, everything is neutral, okay? You have a voltmeter reading of like, basically it's neutral, okay? So now, there you are, you have positive ions forming in your half cell. So your overall charge there will be positive. Okay, so what happens if it becomes positive? Do you think these electrons will want to leave and go to the cathode? Do you think oxidation will occur now? It will stop. It will come to a stop because these electrons now will be attracted to this electrolyte that is positively charged, because opposites attract, right? They won't be leaving these electrons. And what would happen at the cathode? Remember, at the cathode, you originally have these positive cations, and with the incoming electrons, they are reduced. Okay, so as they become reduced, now your positive ions will be used up and it will become metals. So at the end of the day, you'll have your electrolyte there that is filled of abundantly negative electrodes. Negative ions in there. So let's just say you used NO3 nitrate as your electrolyte there. It'll be full of nitrates in there, and then as a result it will be negatively charged. So if it is negatively charged, again, do you think electrons are gonna be in a hurry to come and attach themselves? No, because for one, you will have metal, right? Because those positive ions have reduced to the metal. Then you have an abundance of nitrates in there. So electrons will be repelled by the electrolyte. Okay, and as a result, this whole cell will malfunction. So what does the salt bridge do? It comes to the rescue. It says, okay, on the right hand side, you have, an abundance of negative ions in there. On the left hand side, you have an abundance of positive ions. Things are not neutral anymore. So let me eject my ions so that neutrality can be maintained. So what would then happen is here, where you have a positively charged half cell, you will have your chlorine ions or chloride ions coming in this cell. Okay. To maintain neutrality, because you want a neutral charge. Okay. And then on the other side, let me use a different colored pen. You would have your potassium coming in there because it is negatively charged, right? So you'd want your positively charged ion to go in there and maintain neutrality. Okay, yeah, so I hope that makes sense. So yeah, and that is why I have these notes that, as your metal is oxidized, the cations form, their concentration increases, okay, and the electrons stop moving away because why? They're attracted to the positive charge, okay, and remember the electrons are only moving away because you have a negative potential, hence the anode is negative. But I mean, now if the half cell is positively charged, they won't need to move away, and therefore your function of the cell becomes impaired. And also on the cathode side, or the other half cell, your cations at the cathode reduce to a metal. Okay, so the concentration of cations, they reduce, and you're left now with the electrolyte. In this case, I use the example of a nitrate, and then it becomes less positive, right? It becomes more negatively charged. So electrons, they are repelled to the cathode. They don't want to go there anymore. And as a result, the function of the cell becomes impaired. Now, I just have a tip there that when you are writing the net cell equations, we're going to get to those equations, you need to make sure that when you maintain neutrality, that the electrons are equal. Okay, you'll have, if you look at half cells, like maybe for silver you only require 1 electron. But if you look at copper for one, you are required 2 electrons. So there you have to make sure that you need to balance the equations so that neutrality is maintained. Okay. And now before I get to the standard hydrogen electrode, let's talk about the cell notation. Okay, so let's talk briefly about the cell notation. Okay, so you always start with the anode. Okay, whatever happens at the anode, whatever electrode you have, the electrolyte, you start with that. And then you get to the salt bridge and move over to what happens at the cathode. Okay, you mention the electrolyte, the electrode, etc. Okay, so first of all, you start with your electrode, right? Maybe I say, for example, you have zinc. Okay, so if zinc was your electrode, that would be your solid zinc. Okay, then oxidation occurs. All right, so you went from a solid, and now here your electrolyte, you have an aqueous solution. Okay, so now you have the zinc ion. Okay, so let me just say 2+, for example. So this vertical line that you see here, it indicates a phase change. So you went from your electrode to your electrolyte, okay? Then you encounter the salt bridge, okay? We've talked about the salt bridge, and basically it's indicated by the double vertical lines, okay? They're parallel to each other. Then you go over to the cathode side, the cathode half cell. So there you have your electrode again, all right? Sorry, electrolyte. Start with the electrolyte. Okay, maybe let's go with copper in this case. So you have your copper ions, okay, that are in aqueous solution. Yeah. And then you have your vertical line, which again would indicate the phase change, okay? And after the phase change, we go all the way to the electrode, okay? Again, the electrode would be your solid, okay, because that's where reduction occurs. You go from having your electrolyte or your ions there, and then ultimately you have your solid metal. Okay, so that's basically the cell notation. So one line would indicate phase change, two lines would indicate that you have a salt bridge. Okay, now let us have a look at the standard hydrogen electrode. What is it? Why do we even bother with it? And what do we use it for? Okay, so basically I just want to address quickly the term standard. Okay, so basically we would have to refer to the standard conditions. Okay, so for this half cell, we would have to ensure that standard conditions are maintained. And what are those? Well, firstly, we refer to the temperature, that it has to be 25 degrees or 298 Kelvin. Okay, the concentration would be 1 mole per cubic decimeter. Okay, very important. And then lastly, pressure. Pressure, it really applies if you have gases. If you don't have gases, not really that important, but it has to be 1 atmosphere or 101.3 kilopascal, or you can round it off to 100 kilopascal. Okay, and then now, so the hydrogen gas or the hydronium ion electrode basically was chosen as a reference or a standard half cell. Okay, and if you were to look at your table of standard reduction potentials, you'll actually see that it is, if you look at the E cell or the E naught cell, it would be actually 0 volts. So let's have a look there. Okay, let me pause and look for the table. Okay, so we're looking at table 4A. Okay, you have two tables, 4A and 4B. Basically they're the same, but it depends. Here we're starting with the positive values, then we get all the way to hydrogen. Okay, you can have a look there, it's 0 volts. Okay, and then we get to the negative values. If you wanted to use 4B, start with the negative values, end up with the positive, and there we have our hydrogen. So let us get back to our lesson. What does this all mean? Oh, another thing about this table is it's called the standard reduction potentials. So all these equations, formulas that you see, these reactions basically, they are showing you what happens when they are reduced. Okay, hence it's called reduction potentials. Okay, when they are reduced. Okay, so basically at the cathode, that's where reduction occurs, hence red cat. All right, or we could go to rock. Okay, so basically there where reduction occurs. So if you were to write down the half reaction that happens at the cathode, you just copy these values out or these equations out as they are. But if you were going to look at the reverse, like for example, so the forward reaction would be fluorine plus 2 ions gives you 2 fluorine ions or fluoride ions. Okay, that is what happens when it becomes reduced. But if it becomes oxidized, which is now the reverse, it would be 2 fluoride ions will be equal to 2 electrodes or electrons plus fluorine gas. Okay. All right. So now the thing about hydrogen basically is that if you have a look at it, it has one, it's from group 1, right? If you look at your periodic table, it is the first element and it is from group 1, meaning generally, yes, it has a positive charge. I wrote here that it has an oxidation number of +1, but sometimes when you combine it with some metals, it becomes -1. Okay, so it can swing both ways. It can either be positive or it can be negative, and that's the oxidation number. But also, because it has one electron in its outer shell, okay, it means that it can either gain another electron or it can give away the electron. Again, it goes both ways. Okay, so for it to become chemically stable, like I've written there, it either donates an electron or it gains an electron. Okay, and therefore that's why it is used as a reference, because it can either be reduced on one end or it can be oxidized on the other end. Okay, so let's have a look at what happens there. Okay. Okay, so if we're going to look at this beaker here, just a setup basically for the standard hydrogen cell. So what you have here, you have an opening over here, okay, and you have your hydrogen pumped in. Okay, so yeah, you have your hydrogen gas. The state of it would be gas. It's in a gaseous state. And then this black electrode over here, that will basically be platinum. And the reason why we would have platinum used there, okay, so you can either have platinum as your electrode or carbon, because those are naturally chemically inert. Okay, they don't react, they don't form part of the reaction. Okay, so yes, so you would have a platinum electrode over there. So what would happen is, as you have your gas, hydrogen gas, pumping inside, what would happen then at the electrode there, it could be reduced. Sorry, it would be oxidized, where it would lose electrons. Okay, remember you have two hydrogen atoms, so they have two electrons and they lose the two electrons. Okay, so as they lose the two electrons, they become H plus ions. But also remember your electrolyte that you have, okay, the electrolyte is an acid. Okay, so you know that with acid, it's probably diluted acid, okay, because you have a high concentration probably of water than you do of the acid itself. But it's an acidic solution, an acidic electrolyte. So what we know about acids is, according to the Arrhenius, or let's stick to the Bronsted-Lowry theorem, it donates protons, so H protons. Okay, so we know that we either, if you've looked at the acids and bases video, you either have H plus or you'd say hydronium ions. Okay, so the electrolyte, as it is acidic, it has the hydronium ions. So what would happen then if the hydronium ions come there and come into contact with the electrode? Well, those electrodes, those hydrogen ions will therefore be reduced at the electrode. Okay, and when they are reduced at the electrode, they form H atoms. Now remember hydrogen. Okay, so hydrogen, it comes in pairs. If you remember the Lewis dot structure, okay, it would have to come in pairs. Okay, it can't really go by itself, and therefore that's why you always have H2. Okay, but in this case we're looking at the gas, and that's why you see the bubbles here forming around this electrode, this platinum electrode. Okay, so it's basically the H ions coming from the acidic electrolyte that reduce at the electrode. And also, on the other hand, you have hydrogen gas bubbled inside that actually oxidizes at the electrode. So you have two things happening pretty much at the same time, okay? So that is why, again, hydrogen has been used as the standard or as a reference, okay? So now, what do we do with this information? Basically, you can then use hydrogen, okay, to determine the potential of any other electrode, okay? So it says the potential of any electrode relative to the standard half cell can be measured by connecting it to the hydrogen half cell, okay? So we're going to see, what do we do then if we want to determine the standard electrode potential of a copper half cell? So you can either call it a standard electrode potential, or you can say the EMF or the potential difference. Okay, so how do we then determine the standard electrode potential of a copper half cell? Okay, let's go have a look at copper with the table of standard reduction potentials. Okay, and what role would hydrogen or the hydrogen half cell play in this regard. So remember I told you that this table, it really refers to, if you're looking at the forward reaction, what happens when these chemicals, what happens when these atoms or ions are reduced, and what happens when these solids or gases or liquids are oxidized. Okay, so let's go look for copper. So it is copper 2 plus. Okay, there are various coppers here, so you have to be very careful. Like for one, you have this copper over here, which has an E naught of 0.52 volts. That's not the one we're looking for. You have another copper here at the bottom where it has 0.16. Okay, but the one we are actually looking for is copper 2 plus, which when it reduces to a solid copper. Okay, and it has a positive 0.34 potential difference. Okay, 0.34 volts. Okay, so yeah, so the question I ask here is, what is the natural tendency of carbon? Okay, is it going to be reduced or is it going to be oxidized? Okay, for the fact that you had an EMF or E naught of 0.34 volts, and it is positive. Okay, it's positive. Remember I said those tables actually for the forward reaction show you what happens when reduction occurs. So for the fact that it is positive, it means that it's easy for reduction to occur. So it's easy for the copper, if I were to write it, it's easy for it to be reduced to a copper solid. Okay, so in this case it has a natural tendency to be reduced. So if it has a natural tendency to be reduced, it means that this has to be your cathode. So wherever the copper is, that is basically your cathode. Okay, and with the cathode we know that electrons are flowing to the cathode. Okay, and we know that for the galvanic cell it is positive. Your cathode is positive. But what happens then? So what is the half cell this side? Well, this will be your anode. Okay, so oxygen says, sorry, not oxygen, I don't know why I like saying oxygen, but hydrogen, the hydrogen half cell. Well, hydrogen is like, okay, if you want to be reduced, I'll be oxidized. It's okay. Okay, so in this case, then it has a negative charge. Okay, so the electrons are leaving, so it becomes oxidized. Okay, so that's basically where oxidation occurs. Okay, so in this case, the half cell helps with that. And like we said, the voltmeter reading, or rather the standard electrode potential reading that you would get, would be 0.34 volts. I hope I have that correctly. Yes, it is positive 0.34. Okay, now, so basically now, what exactly is the cell notation? So yeah, what would our cell notation be? Okay, remember I said you always start with what happens at the anode, and then you finish off with what happens at the cathode. Okay, I just added these in. Well, basically, we already discovered that this would be the anode, where your hydrogen half cell is, where inside here you have your H plus ions. Okay, I chose the nitrate as an electrolyte. Okay, so it is acidic. Remember we said it's acidic for the hydrogen half cell. And inside here, still with the same electrolyte, the nitrate, you have copper nitrate solution. Okay, so you have your copper 2 plus ions there that will be reduced to copper metal. And inside your salt bridge, again, I chose potassium nitrate, which will help to keep the cell neutral or maintain its neutrality. So the cell notation, remember you have the hydrogen gas going in. Okay, and also remember we start with what happens at the electrode, or what is the electrode. So your electrode in this case is platinum. Okay, so solid. And then we have the phase change where you have your hydrogen ions in aqueous solution. Okay, so as the hydrogen gas comes in, it becomes oxidized to hydrogen ions. On the other hand, you have the hydrogen ions that can be, but in this case, because at the anode is oxidized, so we're not even looking at what can be at the cathode because we're not reducing anything in this case. So you have your hydrogen ions. Then you have your salt bridge indicated by the two vertical parallel lines. Okay, and then what happens this side? You have your copper 2 plus. Okay, that would be your electrolyte. We do not involve the nitrate because it's a spectator ion. Okay, so and what happens? It becomes reduced. Remember, phase change indicated by that one vertical line. It becomes reduced to a copper solid. Okay, that's basically how the cell notation looks. But now we need to get the net cell reaction. Remember I spoke about the net cell? Well, in this case, you're going to write the half reaction that occurs for oxidation. Remember, at the anode, that's where oxidation occurs. At the cathode, that is where reduction occurs. So I wrote my aura in reverse, like arrow. So at the anode, with the help of the reducing agent, that is where oxidation occurs, or an ox, if you may. And at the cathode, with the help of the oxidizing agent, that's where reduction occurs. So core instead of rock. But it's all good. So let's see. Oxidation, we know that the hydrogen gas has been oxidized to H ions. Okay, so we need to write the half cell reaction. And also, with the reduction, we had copper ions go into copper metal. So let's see. And we know the standard hydrogen potential will be 0. Okay, but what is the half cell? Okay, now remember I said if you're going to read the forward reaction, that is what happens when reduction occurs. But because we are not looking at oxidation, it's going to be the reverse. Okay, so we're going to start with the hydrogen gas and then have the 2H plus ions. Okay, so oxidation, basically you have your hydrogen gas. And you indicate it, please, 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 always indicate it with one arrow. Do not put these, okay, because it is not happening. You don't have reverse and forward reaction happening at the same time. Okay, it's just the forward reaction. So what happens there? Well, basically you have your H plus ions. And what have you lost? You have lost an electron. But we need to balance this because the H ions didn't, or rather you have H2, right, as a gas. So it will produce 2 H ions, which will in return produce 2 electrons. Okay, that's why when you have a look at that, you have 2 H plus ions and 2 electrons. Okay. And then on the other side, we have to now go look for copper. I think I had written the copper, but anyway, let's go see. So here we have 0 volts. So with copper 2 plus, where is it? Okay, yes, there it is. So you have copper 2 plus 2 electrons will give you the copper solid 0.34. So we have 0.34. We have copper 2 plus the 2 electrons. So because this was reduced, we're just going to take the equation as it is. Okay, but indicated with one arrow. Okay, so here we see, remember when I said you must make sure that your electrons are the same for both half reactions to maintain neutrality. Okay, so as you can see here, you have 2 electrons over here and you have 2 electrons over there, so it's basically balanced. So what I can say as my net cell reaction, so I have hydrogen gas and I have copper 2 plus, and with the arrow I can say I have two H plus ions and I have copper. Okay, awesome. And if I were to take it further and ask myself, what would be the voltage or the potential of, okay, so if I were to get the E cell, the potential of the cell, E naught, okay, I would say what happens at the cathode minus the anode. Okay, so at the cathode where there was reduction, we had 0.34 at the anode. So at the end, what the voltmeter reading would indicate 0.34 volts. So that's basically the calculation that you would do to get the E cell or the EMF. Okay, so we're going to look now at example B. How do we basically determine the standard electrode potential of a zinc half cell? So we saw what happened with copper. Copper has a tendency of being reduced. So what about zinc? Okay, what will happen in this cell? So we're going to go and look for zinc and yeah, just see basically, okay, so we see zinc over here. Okay, and you can see that its EMF or its potential difference is negative 0.76. Okay, so if that is the case, what will happen? Remember this table, it shows you the natural tendency of it being, of all these being reduced. Okay, but if we get a negative value, it means that it's actually very difficult for it to be reduced. Zinc, like if you compare it to copper, it's quite difficult for it to be reduced. What happens, what its natural tendency is actually for it to be oxidized. Okay, so let's see. So we know that its potential is actually negative 0.76. All right, so basically it doesn't want to naturally reduce, it would rather be oxidized. Okay, so what would that mean? It means that this would be the anode, okay, where oxidation occurs. In this case, our hydrogen half cell, well, basically that's the cathode where reduction occurs. Okay, so sorry guys, my nose is really blocked. It's so bad. I've tried sprays, but it's not working out. And I thought I would record when it's, perfect conditions, but I'm out of time. So let's do this. Okay, so if at the cathode, your hydrogen gas, well, actually, yeah, you still have the whole process going on. But remember, you had the H plus ions, okay, because of the acid. Remember, you had nitric acid. I've chosen nitrate as the electrolyte. So your H ions, once they, okay, first of all, you have electrons coming in here. Okay, for them to be reduced. So once it gets into contact with the electrode, basically these H ions become H atoms. And ultimately, you have bubbles forming around here because you end up having hydrogen gas. Okay, so that will basically be hydrogen gas. On the other side, the anode, we know that the anode is negatively charged. That's where oxidation occurs. So you have your electrons migrating all the way to the cathode. Okay, so here, because it gets oxidized, you will then start having zinc 2 plus ions that form. Okay, and like we like saying, the mass will start reducing for zinc. Okay, and in this case, you'll just have a lot of hydrogen gas forming on the cathode side. So here we had zinc nitrate. Okay, so yeah, and we have our salt bridge over here. Say salt bridge again. Let's say you have potassium nitrate, and for it to maintain neutrality, you would have the nitrate going to the anode half cell, okay, and you have the potassium going to the cathode half cell to maintain neutrality. So what would be the cell notation here? Well, in this case, we always start with the anode. So we had the zinc electrode, okay, and then we have the zinc. This is the change in phase, so you have the zinc ions. Okay, then you have your salt bridge. So what happened there? You had your H plus ions in your electrolyte. And then you had your hydrogen gas. Okay, then you had your platinum. PT. Had your platinum electrode. Yes. So that would be the cell notation. So now, if I were to look at the oxidation half reaction, well, that is zinc. Okay, I already know that it has a negative 0.76 volts. Okay, so what happens then? You had, if you're going to look at your table again, because it's oxidized, we're going to read it in the opposite direction. We're going to look at the reverse reaction. So it's zinc, and then we have the ions plus the electrons. Okay, you had your solid, and then that solid, due to oxidation, it became oxidized. You have the ions there and the 2 electrons. And also with the hydrogen there, we know that it's 0 volt. So initially you had your H ions, which reduced to hydrogen gas. No. Yes, hydrogen gas. Yes. Hence the bubbles. Okay, because you have H2, you're going to have 2 H ions and 2 electrons there. Okay, so ultimately your net cell equation will become zinc plus 2H, because the electrons are balanced, so it's fine. So you have zinc 2 plus, then hydrogen gas. Okay, so that's basically how you would do it. Okay, so that's how we determine that, the zinc potential is oxidized, and in the previous example, the copper was reduced. Okay, so I hope that makes sense. Okay, now let's talk about the EMF of an electrochemical cell. So how you basically pronounce this uh, zero there, we would say it's a naught. It's actually E naught. So the E naught cell. And I don't know, I didn't say this before, but actually this note here tells you that, the standard conditions have to be complied to. Okay, meaning temperature 25 degrees, concentration 1 mole per cubic decimeter, pressure 1 atmosphere in the place or in the event that you have gases. So if you were to determine what the E naught cell is, or the EMF of the electrochemical cell, you'll basically say the E naught of the cathode minus the E naught of the anode. Like the example I did here when I calculated it, the E cell. Okay. I can also do that for zinc actually, just to show you. Okay. For the E cell, so at the cathode, that's where reduction occurs. We had 0 minus. At the anode, we had negative 0.76. So the reading of the voltmeter would be 0.76 volts. And like I said, with the galvanic cell, you have to get a positive value. If not, you did something wrong. Or instead of saying E naught cathode minus E naught anode, you would go for E naught oxidizing agent minus E naught reducing agent. So when you write the equation in your answer sheet, please write out the full cathode, anode. Don't do it like me here where I just said E cath. Okay, please. And now we're going to talk briefly about the voltage cell potential. Okay, they like asking questions like, we reduced the concentration of something, what would be the reading? Will it increase? Will it increase? Will it stay the same? And why? Okay. Okay, so basically, if they were to ask you questions like that, let's say they started saying, we increase the surface area of the electrode, what will happen to the voltage cell potential? What would be the reading on the voltmeter? Well, basically, the voltage cell potential does not depend on the surface area of the electrode. What it does have an effect on is the current. So if you increase the surface area, like I've put there, SA for surface area, your current will be increased. Okay, and then what would happen to the voltage cell potential is if you increase the temperature, well, the potential will increase slightly. Okay, so if you had 1 volt initially and then increased temperature, maybe it would be like 1.1 volts or something, but it would increase slightly. Okay, so yes, increase in temperature. But now if you were to increase the concentration of either the reactants or the products, this is how you would deal with it. Okay, applying Le Chatelier's principles. Okay, first of all, you would look at your net cell reaction equation. So let's just say this was the net cell reaction. And I'm gonna put it there. Okay, let me just put it there and just circle it in red so that we know what we are referring to. Okay, so yeah, so basically if you increase the concentration of reactants or products, this is what you do. You're going to look at your net cell equation. Okay, let's just say we increased the concentration of zinc ions, for example. So if you increase on the product side, remember the seesaw concept? Okay, so initially everything is in equilibrium. Okay, you have your reactants this side, you have your products. You have your products that side. Okay, and that is your lever there. Okay, so now if you were to increase the concentration of your products for one, this would happen. Okay, you have your reactants up there, you have your products down there because they are more heavy. Okay, so now Le Chatelier says, okay, we need to reach a new equilibrium over here. The products are too much. So what are we going to do? We are going to increase the concentration of the reactant. So your reaction would be reversed. Basically, it would be reactant favored. So what would happen if it's reactant favored? Well, these are the rules that you need to adhere to. If the reaction is product or forward favored, what would happen to the EMF is it would increase. If your reaction is reactant or reverse favored, what would happen is that your voltage would decrease. So in this case, what we are expecting is that your voltage would decrease. Okay, I hope that made sense. And then lastly, well, the voltage cell potential, what would happen if equilibrium is reached? So basically, when the cell or battery is flat, think about when your phone battery dies. Okay, it goes all the way to 0. Okay, it means that the reaction has reached equilibrium. Okay, so therefore the concentration of your cations in the reduction half cell, they have decreased to 0. Okay, nothing is gonna, you basically reached equilibrium. So the forward reaction, the rate is equal to the rate of the reverse reaction. So if that's the case, the EMF reading you're going to get in this case would be 0 volts. Okay. And then now we're going to look at an exam question from 2015. Let me load it up. Okay, so I've loaded the 2015 paper and let's see what it is saying. So it says learners are given the following two unknown half cells. So let me just write down there and see what we have exactly, and see if we can actually notice which half cell is oxidation occurring and which half cell is reduction occurring. Okay, so if you look at half cell 1, okay, based on the notation, first of all, you had these ions, okay, and then they changed phase and became solid. So I would say Q actually underwent reduction. Okay, that's what I would say. And then half cell 2, well, you had your platinum electrode, okay, then you had your gas, and then it ended up being the ions. Okay, so I would say what happened there, I would say it got oxidized. I believe. Okay, so let's see. It's a little bit tricky because if something becomes oxidized, it means it loses electrons. So I'm kind of expecting if it was oxidized for there to be a plus there. But in this case, there's a negative. So let me just leave it at that. Let me not say it's oxidized or it's reduced. We'll see. Let's see what the question says. Okay, so it says during an investigation to identify the two half cells, the learners connected each half cell alternately to a cadmium. CD is actually cadmium. So cadmium half cell under standard conditions. Key standard conditions. For each combination of two half cells, they write down the net cell reaction and measure the cell potential. Okay, so the results obtained for the two half cell combinations are given in the table below. By the way, if you want more examples of the galvanic cell calculations, please do visit our YouTube. You're already on YouTube, but do visit our website as well, where it's all placed in order. But there are more examples that we did, especially from the November papers, the prelims, as well as the June exams. So please do go there and you'll see more examples. By the way, don't forget to like our videos and subscribe to our channel. Yeah. So for combination 1, we see Q2 plus the cadmium solid will give you cadmium ions and the Q. So I would say in this case, Q seems like it was reduced, whereas cadmium was oxidized. Okay, so yeah, and then on the second one, we have the gas and cadmium. Okay, so the cadmium, again, it lost electrons. I would say it was oxidized, but this R, it gained electrons, guys. And the cell potential is actually positive, but that's when they calculated E cell. So yeah, this R it's a guess. So yeah, it's a little bit tricky. But anyway, let's answer the question. So it says, write down the 3 conditions needed for these cells to function as standard cells. Okay, we've discussed this in length. Okay, so it's basically your temperature needing to be 25 degrees or Kelvin, 298 Kelvin. Your concentration, we have gases here. Okay, so concentration would be 1 mole per cubic decimeters, and your pressure would be 1 atmosphere. Okay, 8.2.1. Okay, so for combination 1, identify the anode of the cell. So basically, what was oxidized here? And like I said, the cadmium, it lost electrons, so it was oxidized. Okay, so the anode of the cell, I would say cadmium, or just CD. Now it says identify Q by using a calculation. Okay, so a way in which we're going to do that, we would say that the cell would be equal to what happens at the cathode. Remember to write it out in full. Minus what happens at the anode. Okay, so I know that the anode is cadmium. Okay, so I'm gonna look up what cadmium is. So that's just CD. And there we have it. Okay, so it's basically negative 0.4. So I'm going to subtract negative 0.4. And then I know that, let's go back to the question. Okay, I know that the cell potential is actually 0.13. Okay, so what is the cathode? So that's basically going to be 0.13 minus 0.04, because this negative and that negative will be a positive. So if I take it to the other side, it will be a negative 0.04. So if I take out the calculator, let's just calculate what that would be. Okay, so 0.13 minus 0.04. Yes. Okay, so 0.13 minus 0.04, that would be 0.09. Okay, let me just check again if I had the right value for cadmium. Oh, 0.4. Ooh-wee. Now when you do the wrong things, 0.4. Okay. Okay, so we had 0.4. So let's see, 0.13 subtracted by 0.4, that's negative 0.27. Okay, volts. Now let's go have a look at what negative 0.27 is. Okay, so I see it there. It's actually nickel. So the answer would be nickel. But let's see. Are we answering? I have a tendency of getting answers but not really going back to check if I answered the question. So they want to know what Q is. Yes, Q is nickel. Okay. Now it says 8.3.1. Write down the oxidation half reaction. So for combination 2. Okay, so the oxidation half reaction, basically what lost electrons. That's how you see it. We can see R gained electrons, so no, it was not. It was reduced actually. So the oxidation half reaction would have to be for cadmium, okay, because it is the one that was oxidized. It lost 2 electrons. So we would go from cadmium, the solid, and then we'd have cadmium 2 plus 2 electrons, but we have to go check at the table. Okay, so yes, remember, because it was oxidized, we're gonna write the reverse reaction. So yes, cadmium, the solid, yes, so we have it correctly. And I'm just gonna put it there, although we've written it before, but the EMF is negative 0.4. Okay. Okay, and now 8.3.2. Name or formula of the metal used in the cathode compartment. Okay, so this was oxidized, so this is the anode compartment. So in the second one, but it's only for 1 mark. I feel like I need to do a calculation here. Oh. So guys, in our cathode compartment, we can see that R was reduced, right? It gained an electron, and we can see that R is a gas. So if you have a gas, it means that the metal that was used in the cathode compartment, that could have been platinum. Remember in our hydrogen half reaction, that standard electrode cell, we use platinum because we're dealing with the hydrogen gas. So yes, platinum. Okay, hence it's 1 mark. All right, and then the last question. Arrange the following species in order of increasing oxidizing ability. So what does it mean when they say oxidizing ability? If we look at our table here, okay, so it says increasing oxidizing ability. That is pretty much on the left hand side. Okay, and then on the right hand side, as you go down, it says increasing reducing ability. So I like to say, if I say oxidizing ability, that's basically saying as you go up, the reducing agents oxidizing ability would mean oxidizing agent. So as you go up in this table, table 4A, the reducing agent strength increases as you go up. Okay, if you go down on the right hand side, it says increasing reducing ability. So the reducing agent in this case is the strength of it is reducing as you go down the table. Okay, so on the left hand side, if it says oxidizing ability, that's basically saying it was reduced. So if you go up the table, like fluorine, which is number 1, it reduces the best. Simply put, okay, it reduces the best. So let's get back to our question. Okay, we have Q, right? Q, we already determined that it is nickel, right? Yes, 8.2.2. So Q is nickel, and its EMF was negative 0.27, right? Yes. Then we have R. We actually don't know what R is, but it's a gas, okay? R2 is a gas. We can actually, how many marks is this? 4 marks. So I would actually calculate and see what actually R is. So I know I have cadmium, and in this case, cadmium was oxidized. So if I were to get the E cell, in order to get R, okay, I'm gonna abbreviate here. I have the cathode minus the anode. Okay, so I had 1,76. The cathode, that is where what I'm looking for, where there was a gain of electrons. And the anode is for cadmium, which is negative 0.4. So basically, I have 1,76 minus 0.4. So that should be 1,36. So what is that? What is 1,36? Chlorine. I don't know if you see this, but 1,36 is chlorine gas. Okay. Okay, so we have R2. We know that it is chlorine. So let me just put it here again. It's actually chlorine. And the EMF there is 1,36 volts. Okay, and then lastly, what do we have? Oh, we have cadmium. Okay. Okay, so cadmium, it had an EMF of negative 0.4. Okay, so now it's saying arrange the following species. Oh, they said a calculation is not required. Okay, I calculated. All right, so we're gonna have to, yeah, this, man, it's fine. Okay, so we're gonna have to discard this calculation that I did and wasted time on. Okay. But basically, what I would recognize about R is that R was reduced, okay? Q and cadmium were oxidized. So this basically R was reduced. Okay, so since we're not considering, we don't know what R is, we know but we don't know, okay? This was oxidized cadmium as well as nickel, it was oxidized. Okay, but if it says arrange the following species in order of increasing oxidizing ability. So like I said, if they tell us about oxidizing ability, that's basically the same as saying oxidizing agent. Okay, which in turn means that which one is actually increasing, which one is reduced more. Okay, let me just blow my nose. So yeah, basically, which is the oxidizing agent, but what we're looking at is which one was reduced more. And our EMF will actually tell us you had cadmium that was okay. Okay, no, what am I saying? So arrange the following species in order of increasing oxidizing ability. Okay, so basically which one was reduced more? The only one that was reduced, guys, is R2. Okay, but you know what? They said a calculation is not required, but they didn't say don't calculate. So we already know we have chlorine. So we know chlorine was definitely reduced more. Okay, and then what? Which one was oxidized more between cadmium and Q2? Basically, which one has the higher negative value? That would be cadmium. It was oxidized more. So it would be number one. Okay, so leaving Q as number two. Actually, let me just put it like they required there. So instead of chlorine, I would put R2. Okay, so that's R2. So yes. Now they say explain fully how you arrived at the answer. Well, basically, guys, what I did, I'm just going to say it in words. What I did, I compared the EMFs. Okay, if it was negative, it means that it was oxidized. Okay, so hence the ones that were oxidized, I wrote first. Okay, I know that R2 was reduced. We did the calculations, so we managed to see that. So hence R2 is reduced. Okay, so we also refer to the table of standard reduction potentials. And you can see on the table which one is reduced, which one is oxidized. And as a result, R2, which is chlorine, was the one that was reduced, basically better. So I think, first of all, explain what oxidizing ability means. I told you it's the same as saying oxidizing agent, okay, meaning that reduction occurred. So basically the question was what was reduced more. So I would explain that. and then I would put it in order by referring to the table. Okay, so yeah, I hope that makes sense. And yeah, that's it for this lesson. See you again next time, and please don't forget to like our videos as well as subscribe to our channel. Okay, bye.